Thank you so much for the invitation to speak here. It's my pleasure. So I'll be talking about some joint work together with my collaborator, Jason Altschuler, who's at Mortenstadts. And this will be a local error framework in KL divergence. I'll kind of explain what that means. And so this talk will be about, I guess, the theory of MCMC. And when I do theory, I'm very inspired by the theory of convex optimization. So this will be kind of the setting in which I naturally look at these problems. So just to draw the analogy, in optimization, we have this basic algorithm, which are all formed from discretizations or variants of the gradient flow. And we know that the gradient flow under conditions such as convexity will converge to a global minimizer. And the analogy in sampling is the Langevin diffusion, the solution to the stochastic differential equation, which converges to a known stationary distribution, and then turning that around, we can use this diffusion to sample from the desired stationary distribution. So this is the picture in continuous time, but in order to actually implement these kind of algorithms on a computer, we need to also look at discrete time. So in optimization, the discretization of gradient flow is gradient descent. And the nice part about gradient descent is that if I take the same conditions as required for the continuous time dynamics to converge, but I also add some extra smoothness assumptions, then I still get convergence to the global minimizer. However, as we know, one major issue in MCMC is that when we discretize a diffusion process, then the algorithm becomes biased in that the iterates of this algorithm form this discrete time Markov chain, whose stationary distribution does not in general equal the target distribution pi. So because of this extra complication in the world of sampling, one important issue is to kind of quantify the amount of bias that discretization incurs. This is kind of a large part of the study of MCMC. And of course, there are ways that to correct for this bias. Most notably, there's the Metropolis-Hastings correction. So this talk will not focus on this at all. We're solely going to focus on the problem of controlling this bias. Okay, so getting into a little bit more details. So this is perhaps the simplest setting for optimization is if your function f is strongly convex and smooth, then the iterates of gradient descent are actually contractive. So if I measure the distance between two iterates in the Euclidean norm, then there's some constant c less than 1 such that the next distance is at most c times the previous distance. And for this talk, I will not really worry about the dependence on alpha, beta, the condition number. I'll focus on the dependence on the dimension and the accuracy. But of course, like all these kind of dependencies are spelled out in the paper. Okay, so analogously, if we adopt an analogous assumption for Langevin, which is that the Hessian of the potential is lower bounded and upper bounded, then again, we have contraction where this contraction occurs in the Wasserstein distance. If I measure the Wasserstein distance between two copies of this algorithm, it contracts from the previous Wasserstein distance. However, like this only implies that two copies of the algorithm converge towards each other. You still have to address the bias. So then if you do some standard analysis of the bias, what you can show is that under these minimal assumptions, you can get epsilon error to the desired target distribution pi with the number of iterations that scales something like d over epsilon squared. And you could do a little bit better with higher order smoothness assumptions, but under this kind of assumption, this is the known result for LMC. So this is all for the most basic discretization of the Langevin diffusion. So now let me go to a more advanced discretization, which I'm quite interested in. So this is this amazing discretization due to Rochi Shen and Yintat Li in 2019. It's called the randomized midpoint method. So the randomized midpoint method is written here. So the way it works is that we draw a uniform random variable, un, uniform between 0 and 1. And in the first step, what we do is we take a step of the Langevin discretization, but only for step size equal to un times h. Okay, so this is basically taking a Langevin step with random step size, a uniform between 0 and h. Okay, and we add the corresponding amount of Brownian increment. And then what we do is to define our real next iterate, we perform this kind of Langevin step, but the gradient of V is evaluated at this intermediate point up here. Yeah, is there a question?
Sorry, that's a mistake by me.
Oh, okay. Yeah, and one very interesting feature of this algorithm that's crucial for its performance is that these two Brownian increments are correlated with each other, but you can, of course, sample correlated Brownian increments, so it's still implementable. Okay, so why does this discretization actually improve upon the standard one? Here's a little bit of intuition. So suppose I take the expectation over this uniform random variable where I fix everything else. Then what happens is that the effect of taking the expectation over grad v evaluated at this point, you should think of x plus as being as kind of living at a random time. And what I mean by living at a random time is that's how much of the corresponding Brownian motion I've added to this process and how much of the gradient I've added. So if I take the expectation over un, this becomes a continuous integral over xt plus, where xt plus is defined in the same way as x plus on this first line here, but replacing unh with t. And then we have the Brownian increment. So one very nice thing about this expression is that this expression looks very similar to the continuous time Langevin diffusion. The continuous time Langevin diffusion also integrates the gradient over time. The only difference is that here, like instead of xt, you have xt plus, where xt plus is this intermediate point formed by this preliminary LMC step. But the intuition is that in expectation, this process should be much closer to the continuous time diffusion, so the discretization error should be less. Now, like one objection you might raise is that, well, why am I allowed to take the expectation over un? When I run this algorithm, I only have one specific realization of the uniform random variable un. So why is it the case that this intuition still helps me improve my performance? And the reason for that is this kind of intuition, what it tells me is that the algorithm has less bias. So bias is kind of taking the expectation over un. And then if I speak of bias, then you might also think that another component of the discretization error is the variance. So to kind of make this precise, all of this is founded on this simple intuition, which is suppose you have a sum of n random variables, each with mean and variance sigma squared and their IID. Then the approximate size of this sum would scale as n times m. So this is the deterministic error, which adds up linearly. And then you have the stochastic fluctuations, which we know kind of cancel each other out. And so this part only scales as n to the 1/2. Okay, now the errors that we make at every step of a discretization method are definitely not IID random variables, but you might expect that there's a similar kind of intuition that holds for them, and that there's a deterministic component that adds up linearly over the iterations, and then some stochastic fluctuations that will cancel out. And you can also kind of think of this as a bit more formally as if I condition on everything that happened before, the next discretization error, like this might form some kind of martingale difference sequence. So to make this a little bit more precise, suppose that starting from any point little x, there's some ideal process that we're interested in, which produces this capital X that we want to simulate, but we apply a discretization method that produces x hat. Then let me define the weak error. The weak error is going to be the bias incurred by the discretization. So this is when I put expectations on both of these and then measure the difference. And then the strong error is going to be an upper bound on the variance. It's just going to be the L2 norm of this difference. So if this kind of intuition from before is correct, then we might expect that the error after capital N steps scales as n times the weak error, the deterministic part, plus square root n times the strong error. And this is the stochastic fluctuation part. And when the weak error is smaller than the strong error, this should be a much better bound than just naively adding up the strong error capital N times. And indeed, you can make this formal through this framework called local error analysis. So local error analysis is kind of standard tool in this field. You could see an entire book about this method by Milstein and Tretyakov, for instance. So here's one kind of formal instantiation of this idea, is that let's say I have p hat and p two Markov kernels. P hat is my discretization, and starting at little x and little y, the algorithm started from x produces x hat, and then the ideal process started from x and y produce capital X and capital Y respectively. Then I'll have these assumptions. I have a bound on the weak error, a bound on the strong error, and I also want the ideal process to contract so that the errors will not accumulate indefinitely over time. And then there's this extra technical condition, which is needed for the proof, but I kind of encourage you to ignore it for the purpose of this talk. So typically gamma is going to be some small parameter, so it doesn't affect the final bound much. Then if I define the effective time horizon, so the effective time horizon is the minimum of n and the number of steps governed by the contraction rate, then what you can show is that the Wasserstein distance between these two processes after n steps behaves like one term, which when L is less than 1 decays exponentially fast from the contraction. And then what you see is, so the squared error behaves like n squared times the square of the weak error plus n times the square of the strong error. So this kind of captures the intuition that we were talking about before. So when you apply this to the randomized midpoint discretization, for instance, you can compute these various parameters. You find that the weak error is indeed smaller than the strong error, and this is because of the cancellations given by this uniform random variable. So because the weak error is smaller than the strong error, we expect to be able to gain from the local error framework. And indeed, if you plug in all this and compute the final bound, you could show that you can achieve epsilon error after n steps. But now the iteration count is the square root of what it was before, square root d over epsilon. So that's a significant improvement over the basic discretization of Langevin. In fact, there's some evidence due to this paper of Kaolu Wang that this is maybe an order optimal discretization of the basic Langevin diffusion. So I think this is a really nice theory. It starts off with this simple intuition about how the discretization errors should behave. And it takes that intuition, turns it into a rigorous framework that's easy to apply. The reason why it's easy to apply is because these assumptions of weak error and strong error, these are local assumptions, only having to do with how the discretization method behaves in one step. And based on these local assumptions, then you get this multi-step bound, which in many cases seems to be sharp. So based on that, maybe one question is like, why am I talking about this? What's there kind of left to do in this subject? And really, this talk is about the choice of performance metric. So everything I've been talking about is really for this Wasserstein distance as our choice of metric. And in this talk, what I really am interested in is how to extend all of this to the KL divergence or the relative entropy, which is a stronger notion of metric. So let me just spend a little bit of time motivating this. So let me start with the obvious, which is that KL divergence is a more stringent metric than the Wasserstein metric. So in this case where all the measures are strongly log concave, we have Talleyrand's inequality, which says that KL upper bounds the Wasserstein distance. So KL is indeed stronger. But by Pinsker's inequality, KL divergence also upper bounds the total variation distance, and total variation is actually the standard definition of mixing time. So it would be desirable to have guarantees there. And really, there's a qualitative difference between W2 and KL because I can have the W2 distance be finite between two discrete measures, for instance, or between a discrete measure and a continuous measure, but the KL divergence would become infinite. So what this says is if I have a KL divergence guarantee, it ensures that the law of my iterate has some regularity, that it has some kind of density with respect to the Lebesgue measure, and that this density is kind of nice in some sense. Okay, and if I have a certification that the law of my iterate is more regular, then by duality, this means that I get a closeness of test functions for a broader class of test functions. So in particular, if I have just this W2 guarantee, this would tell me that the expectations of test functions are close between these two measures, save for Lipschitz functions. Whereas if I have a total variation guarantee, then I would see that this expectation is close for all bounded functions. And bounded functions are generally larger class than Lipschitz functions. So an example of this last case is if I take f to be an indicator function, so that's supposed to be an indicator. I guess it's not rendering for some reason. But yeah, if I take an indicator function that's a bounded function, but not a Lipschitz function, and this is the kind of function that I would need for an application to constructing credible regions for Bayesian inference. Okay, so that's one basic motivation, is that KL divergence guarantees are kind of qualitatively stronger and in some cases more useful than just Wasserstein guarantees. But there's actually a broader reason why I care about KL divergence. And it's because of this perspective of sampling as optimization, which is maybe starting from this seminal work of Jordan, Kinderler, and Otto, and continues to inspire a lot of my research. So what they put forth is that the problem of sampling can really be viewed as optimization of this KL divergence functional over the space of distributions, where you equip the space of distributions with a Wasserstein metric. So they started drawing this dictionary that links concepts from these two fields of optimization and sampling. So instead of minimizing some function over Euclidean space, we now try to minimize this KL divergence. And the Euclidean distance is replaced by Wasserstein, and the analog of the gradient flow is the Langevin diffusion in a precise sense. In that, like if I take the gradient flow of this KL divergence with respect to the Wasserstein metric, I do get the Langevin diffusion. And a lot of my work is kind of trying to extend this dictionary further. So in this picture, the KL divergence is a very natural metric to look at because it's the objective function that we're trying to minimize over the space of distributions. And if we push this analogy a little bit further and see what convex optimization tells us. So in convex optimization, we can study convergence of the gradient flow under these kind of assumptions. If f is strongly convex, then we have exponentially fast convergence. If f is just convex, but not necessarily strongly convex, you get a 1/t decay. And then if f satisfies this Polyak-Loja-Siewicz condition, or PL inequality, so this allows for non-convexity, but it says that the gradient norm always upper bounds the objective gap, so the gradient flow continues to make progress. So under this condition, then you still have exponentially fast convergence. And there's an exactly analogous picture for the Langevin diffusion, where the first two cases correspond to the potential V being strongly convex, or convex but not necessarily strongly convex. And the PL inequality is analogous to pi satisfying a logarithmic Sobolev inequality. Okay, so one thing maybe that you should notice from this slide is that in this very first line, in the strongly convex case, what we have showing up is the Euclidean distance, or the Wasserstein distance, which is the kind of stuff we've been looking at so far in this talk. But every other result in this table really relies on looking at the objective gap or looking at the KL divergence, which is kind of why we want to extend KL divergences to cover these cases. So now again, if we move from continuous time to discrete time, then in gradient descent, we have these results, and this should look pretty much identical to the previous slide. I've just replaced the continuous time variable t with the iteration count n. And that's really the remarkable and amazing fact about convex optimization, is that discretizations of the gradient flow achieve exactly the same results as the continuous time dynamics if you discretize suitably. That's an amazing success story of convex optimization. And now I want to know what we can say about sampling. So for sampling, essentially like the framework that I showed you before, this local error framework, it handles the case of W2 guarantees in the strongly convex case. Namely, it certifies that you have some exponentially decaying dependence on the initialization, plus a tight control on the bias starting from these local assumptions of the discretization method. Because in sampling, we have this extra issue of the bias to worry about. But what I want to kind of argue is that because this local error framework was only telling us something about the Wasserstein distance, we do not have a systematic framework for getting results in all of these other cases. So thus far, I would say that proving guarantees for these other settings has been sort of case by case. So there are some techniques to try to get these results that hold in KO divergence or other metrics. But just as an example, none of the methods that I'm aware of have been able to prove KL divergence guarantees for, say, the randomized midpoint method. So for the randomized midpoint method, we would just not know how to get the Sharpe rates for these like question marks here. So just to reiterate, because this is kind of the point of my talk, is aside from this strongly convex setting, for which the W2 local error framework provides this satisfactory framework for getting good control of the bias of the discretization method, what we lack is kind of a unified framework that would allow us to derive all these complexity bounds for like all the other cases of this table. And so that brings me to the main result of this work, which we put it out in this paper, Shifted Computation 3. So what we do is we provide exactly this kind of local error framework in KL divergence. So here's the statement of the theorem, slightly simplified. So we're going to assume that all of the local error assumptions from the W2 framework continue to hold. So just to remind you, those were four assumptions. There was the bound on the weak error, bound on the strong error, the contraction of the ideal process, and also this technical condition that I swept under the rug. And for KL divergence guarantees, we need to add on two more assumptions, which pertain specifically to KL, which are regularity and cross-regularity. I'll talk about them in just a second. And then, so assuming that this holds, then we get this KL divergence bound after n steps of the algorithm. So I'll kind of try to break down this bound slowly, but first let's talk a little bit about the assumptions. So this first assumption of regularity, this measures what the KL divergence is if I run the ideal process started from two initializations, x and y, and I want this KL divergence to be bounded by the initial square distance between x and y. So this is capturing some kind of regularizing effect of the diffusion, in that even if I start from 2 point masses, after some time, their laws will become absolutely continuous with respect to each other. So this turns out to be a pretty standard fact about many diffusions. So in some sense, this assumption will just come for free. And this will also be discussed later in this talk. The other assumption called cross-regularity. So this requires bounding the KL between the algorithm started at X versus the ideal process started at Y. This is kind of a non-standard assumption. And in fact, it's pretty challenging to check in some settings. So in this paper, we spend a lot of time discussing how to check it, but there are some ways to try to check this. Although so far they've been a little bit ad hoc. But the good news is that in some sense, maybe in a sense to be made precise later, this final bound that we wrote down, it pays for the regularity assumption, capital N minus 1 times, and then it only pays for cross-regularity at the very last step. So even though this is kind of a difficult assumption to check, especially to get the tight dependence on these parameters like B, it kind of shows up in not a severe way in the final bound, which turns out to make it kind of okay. All right, so now let's talk about the bound on the error. So first I want to talk about this factor that shows up in front of this Wasserstein distance. Okay, so when L is less than 1, I get something exponentially big in the denominator. So this implies that the dependence on the initialization decays exponentially fast, which is what we expect in the contractive case. So that's good. But even when L equals 1, this still makes sense. of course, the expression kind of becomes an undefined ratio, but you should interpret this ratio as the limiting value as L tends to 1. And when you compute this limit, it becomes 1 over capital N. And notice that this 1 over capital N, this is exactly the kind of decay we expect in the convex but not strongly convex case. So this bound captured that. And then finally, when L is bigger than 1, none of the terms in this bound actually blow up exponentially. Because when L is bigger than 1, this term in the denominator, this will just vanish. And this whole expression converges to the ratio L minus 1 over L, which is not blowing up. So in fact, it turns out that even in the case L bigger than 1, this bound is still very useful. In that case, what you can interpret it as for kind of experts in the audience is that this is a variant of Girsanov's theorem for controlling the KL divergence, but it's a version of Girsanov's theorem that takes into account the weak and strong errors. So, and also like it should be noted that these two cases of L equals 1, L bigger than 1, these cannot be covered by the W2 analysis because the W2 local error analysis implies that the errors kind of grow too fast in these two settings. And then finally, the kind of point of doing this local error framework is to witness the fact that the strong error accumulates in less rapidly than the weak error. And you can see this from the bound because the strong error has one less factor of n appearing in front of it. Okay, so that's kind of the bound and the assumptions. Kind of the point is somehow like in all the situations where we were able to apply this W2 local error framework, now I won't say that it's immediate to get a KL bound out of it, but at least there's kind of a systematic way to try to get a KL bound through this framework. So now, like if I apply this to this motivating example I had of the randomized midpoint discretization, so this is what we can prove. In this strongly convex and smooth setting, for instance, you can now get KL divergence guarantees for the randomized midpoint method, and the number of iterations is what you'd expect. Okay, and yeah, so this is perhaps the main application that we have in our paper. This problem of trying to get KL divergence guarantees for randomized midpoint is something that's bothered me for many years now. So I'm pretty happy to have done this. So one of the challenges of trying to analyze randomized midpoint is like there's many ways you could try to interpolate this as a continuous time process, but it's not naturally a Markov process. Like looking at this uniform random time, um, how should I say this? Like the gradient is evaluated at this uniformly random time. And so like if you try to do a continuous time interpolation at the beginning, you might find that the gradient is looking ahead into the future. This kind of breaks a lot of previous approaches for studying KL divergence, like Kirsanov's theorem and so on. Which is why I think this framework is pretty powerful. Let me also mention, so part of my motivation was that this KL local error framework can go beyond this strongly convex case, and indeed we can prove results for the randomized midpoint discretization, both in the convex case and also the LSI case. In these settings, there were kind of no previous results known for randomized midpoint. Okay, so that's kind of the summary of the main result. Now would be a great time to ask any questions if you have any, because I'm about to kind of dive into technical details.
Sinho, can I ask a quick question on the optimality? It seems you hint the bounce you get is probably optimal, but can you comment a bit more on that? I think you give a reference to the previous papers. Yeah, order optimal.
Yeah, so they considered a framework which is known as information-based complexity. In this framework, you imagine that there's a true trajectory of the Langevin diffusion, and you want to actually get close to that true trajectory in a pointwise sense. And what are you allowed to do? You are allowed to kind of query the gradient of the potential, And you are also allowed to query certain increments of the Brownian motion that's driving this trajectory. And then based on that information, you have to get pointwise close to that trajectory, or at least in a mean squared error sense. And within that framework, they were able to show a lower bound for discretization of the Langevin diffusion. Okay, maybe not in this paper, but in a follow-up work, which matches the upper bound given by randomized midpoint. So this is some evidence that says if your goal is to discretize the Langevin diffusion, then this randomized midpoint method is optimal under these assumptions. Now, let me say a little bit about what this lower bound doesn't say. So first of all, it doesn't say that the Langevin diffusion is the optimal stochastic process to discretize. In fact, we know that the kinetic Langevin diffusion performs better. It also doesn't say that such an algorithm would be the best possible algorithm for sampling, because for all we know, the optimal algorithm for sampling might not even involve discretization of a continuous time process. So to really answer this question of lower bounds for sampling, which I'm very interested in, you'd have to prove a lower bound against all query algorithms, which has been pretty difficult so far. But yeah, you can just loosely interpret this as evidence that this is a pretty good discretization method.
Oh, great. And just to make sure, all the optimal means they are matching the square root of d over epsilon, so match both the dimension and the accuracy level.
Yes.
Okay, cool.
Any other questions? Okay, if not, then maybe I'll delve a little bit into the ideas that go behind this. Okay, so before talking about this paper, Shifted Computation 3, of course, there was a Shifted Computation 1. And in this first paper in the series, we considered a case where the two kernels we're comparing are the same. So this corresponds to looking at two copies of the idealized process and asking how their KL divergence behaves. So this is a really good case to look at. It's already a pretty interesting problem. So as a warm-up, if I consider two just Gaussian random variables, then how can we upper bound the KL divergence between these two Gaussians? So the answer is there's a closed form formula for the KL divergence between Gaussians. You can find this on Wikipedia. And you'll see that this KL divergence is just the square norm of x minus y divided by 2 sigma squared. Okay, so that's a basic fact. But it already implies something interesting because you can combine this with the joint convexity of the KL divergence with respect to its two arguments, plus some coupling argument. And when you do that, you can upgrade the statement to the following one, where if I have these two Gaussians, but they start from random initializations, then the KL divergence is bounded by the initial Wasserstein 2 distance squared between the initializations, divided by 2 sigma squared. So this kind of bound, where we're bounding KL divergence in terms of the initial Wasserstein, this is kind of the one-step version of the bounds we're after. So now the real question we want to address is multi-step. So say that we have two stochastic processes, which let's just take the discretizations of Langevin, for instance. So in each of these processes evolves by the mean is some function of the previous random variable, and then I add some fresh Gaussian noise. And now how do I bound the KL divergence between these two processes at time capital N? So maybe if you asked me this question, I don't know, 2, 3 years ago, my first instinct, or pretty much anyone who works in information theory or with KL divergences, their first instinct might be to use the chain rule for the KL divergence. So let's see what happens when you do that. Okay, so first of all, I have the KL divergence between these two processes at time n. By the data processing inequality, I can bound it by the KL divergence between the full trajectories. And then once I have the KL between two trajectories, I could apply the KL chain rule. But these two processes have the same conditional distributions. They're evolving by the same Markov kernel. So the chain rule just gives me the initial KL divergence. Okay, fine. So this is called the data processing inequality along a Markov chain. It says that the KL divergence can only decrease. But so that's an important fact, but it doesn't tell us all that much in this context. For instance, if I start from deterministic initializations, this bound would give me infinity. But I know that this KL divergence bound probably shouldn't be infinity because after n steps, these two random variables are going to have nice continuous distributions that have finite KL with respect to each other. Okay, so but on the other hand, on the previous slides, I showed this alternative strategy of getting a one-step bound. Okay, it says that if I have KL between two Gaussians and their mean is just like applying this mapping, identity minus h times the gradient, then I have a closed form expression for what this KL divergence is between two Gaussians. So this tells me how the KL behaves in one step. Now the question is kind of how do I compose together bounds, one-step bounds such as this to get a multi-step bound? And the answer is really to combine both of these two ingredients together, the KL chain rule and this one-step bound. So this is the key idea that underlies all of this, is the definition of an auxiliary process. Okay, so we define this auxiliary process x prime, which starts at one of the processes, but we continually shift the auxiliary process to make it hit the other process exactly at time capital N. And the reason why we do this is that if we're only interested in the KL divergence between xn and yn, that's going to be the same as the KL divergence between xn prime and yn if I make xn prime exactly equal to xn. So, and now like the reason why this is helpful is because when we apply the KL chain rule, we could do it along this auxiliary process instead. So this is kind of just saying what we cared about in the first place is the KL between the marginals at time n. So instead of doing the chain rule along the original trajectory, we could really choose any trajectory that ends at the same two endpoints and apply KL chain rule there. So how do we apply the KL chain rule? We need a twist of it. So this was a KL chain rule that we've been using before, is that the KL between the y marginals would be bounded by a KL between joint distributions. And then once we have the joint distribution, we apply the KL chain rule to get the KL between the x's and then the conditional KL. So what we introduced is just a little variant of this, which is suited for analyzing this auxiliary process. So again, we start with the KL between the y's is bounded by, but now we put the KL between the law of x prime and y versus x and y, where x prime is any random variable that I can choose. So this is still true because the marginal of this joint distribution is still mu y. The marginal of this second joint distribution is also nu y. So this is still a valid use of data processing inequality. But now if I apply the chain rule here, I get the KL between mu x prime and nu x plus, and now like you get a different term for the second term. Okay, I get the KL divergence for the conditional at x versus x prime. And this is integrated over any coupling of x and x prime from these distributions, mu x and mu x prime. So one way to think about it is, even if your process starts from x and goes to y, this is saying I can kind of change the history of this algorithm, pretend that instead of coming from x, it came from some other random variable x prime, but I have to pay this price for doing so. And this price I have to pay is some kind of coupling cost. Okay, so in our first paper, this is the theorem that we prove, which holds for any Markov kernel satisfying these assumptions. The first assumption is this one-step KL regularity. And the second assumption is that the process is Lipschitz with respect to the Wasserstein metric. And under these assumptions, what we get is this sharp n-step bound for the KL divergence. So it's sharp in the sense that there's there's a Markov kernel, in fact, like Gaussian kernels that satisfy these assumptions, and then for those processes, this bound becomes equality. So just as one quick note, under these assumptions, there's something kind of trivial you can do, which is you can start with this regularity assumption. This regularity assumption converts you from KO divergence in one step to Wasserstein distance. Once you have Wasserstein distance, now you can apply this Wasserstein-Lipschitz assumption a bunch of times. So the bound you will get looks something like that. But when your process arises as a discretization of a continuous time process, then this kind of bound is actually vacuous as you let the step size tend to 0. And that should make sense because this argument is only exploiting regularity from one step, whereas like we know that the diffusion adds regularity at every step. So really the question here is like, how do you get the optimal bound? So let me quickly kind of go over this proof sketch. Okay, so we have our original processes, xn plus 1, yn plus 1, which are evolving by this Markov kernel P. And now we define our auxiliary process. So this auxiliary process is going to be called x prime. In the first step, to update x prime, what we do is we shift it towards the process x that we wanted to hit. Okay, so we take a convex combination between x prime and x, which brings it closer. And then we apply the kernel P, starting from there. Okay, and then we want to choose this sequence of shifts so that the auxiliary process exactly hits xn at time capital N. So assuming that this condition is satisfied, now what we want to do is bound the KO divergence between the auxiliary process and the second process y. Okay, so x prime, we applied p to x tilde, and y, we applied p to the previous y. So this is what the chain rule would give us for KO. But again, like this KO chain rule is not useful, which is why we introduced the shifted KO chain rule. So in this shifted KO chain rule, I changed this first argument here to be xn prime so that I would actually get a recursion for the KO. And then the price for changing this means that I have to pay this coupling cost for the second term. Now this coupling cost, this is good because I can apply the one-step regularity assumption for the KO divergence between these two kernels. And it becomes some squared distance. And if you look at the definition of xn tilde, which is a convex combination, you get to this. Okay, so this is kind of a one-step recursion for the KO divergences where you just add up a bunch of terms that involve these squared distances. So the other thing you need to do is obtain a recursion for these square distances, and this you kind of obtain using the assumption that this kernel is Lipschitz with respect to the Wasserstein distance. And so you obtain this other recursion. So you solve this recursion for the distances, you plug that in to the recursion for the KL divergences, and then the final step is to optimize over the choice of these shifts, eta n, and that would give you the optimal bound. So maybe let me just give a little bit of, okay, this is what you get when you apply this to the Langevin or discretization of Langevin and you let step size tend to 0. If you have a lower bound on your Hessian, which is allowed to be negative, then you get this sharp bound on the KO divergence. In particular, when alpha is bigger than 0, this decays exponentially fast. When alpha is 0, this decays like 1 over capital T. And then it still also makes sense when alpha is negative. And one feature of this kind of bound compared to log Sobolev inequality is that log Sobolev inequality would require finite KL at initialization. So I would not be able to initialize at a point mass. But this kind of bound, because it depends on the Wasserstein at initialization, I can initialize from a deterministic starting point. So just a bit of history about this. So we call that kind of inequality a reverse transport inequality because it's upper bounding KL in terms of Wasserstein instead of the other way around. So this kind of bound was first proven by Fengyi Wang in 1997, a really nice paper. And then the KL version was kind of also shown in this paper by Bobkov, Gentile, Ledoux. And these original proofs were based on Markov semigroup theory. There's another proof of this theorem which comes from this paper by Arnaudon, Dalmier, and also Fengyu Wang, which is a coupling proof based on Girsanov's theorem. And this coupling proof is actually the continuous time analog of the proof that I just showed you. Now, like this inequality by Fengyu Wang has become very influential. It's used a lot in the theory of stochastic processes. Now, in a completely different corner of the world, there was this paper in the theoretical computer science community by Feldman et al. And they introduced this object, which is known as shifted divergences, and they were studying this problem of differential privacy. Like, how do we make our algorithms not leak sensitive information about the users in our database? And this technique of shifted divergences turns out to be very connected to this Girsanov coupling proof. So my collaborator, Jason Altschuler, he was also interested in privacy. He did this internship at Apple. And while he was there, he was studying this shifted divergence object, and with some collaborators and also with myself, we were exploring the use of this tool for privacy and sampling. And this work on shifted computation 1 is really bridging together these two literatures. So on one hand, our work kind of gives an information-theoretic interpretation of this coupling proof and also extends it to hold for any discrete time Markov kernel, satisfying our two assumptions. And then by connecting this framework of shifted divergences to this literature on diffusions, kind of gives you a better understanding of this technique from differential privacy. Okay, so I mentioned that this inequality by Fengyu Wang was pretty influential for studying stochastic processes. Why is that the case? It's because by duality, they're dual to these functional inequalities known as parabolic Harnack inequalities. So functional inequalities are kind of inequalities that hold for all functions f belonging to some class. And as some of you might know, this is kind of the start of this deeper story, which connects together diffusions and curvature and concentration and so forth. So the reason why I'm mentioning this is just if there is a shifted computation 1 and also a shifted computation 3, then what happened in shifted computation 2? And the answer is like our second paper was really more related to this literature. So as an example of what we proved like this other sharp inequality for the Langevin semigroup, which you could, if you're interested in these kind of sharp inequalities, you're welcome to check out the paper. But it's kind of not very relevant to the focus of this talk, which is eventually about bringing this story back to analysis of discretization methods. Then finally, like going back to shifted computation 3, the main difference between the first and third paper is that we need to consider this case where the two kernels are different, because you have this discretization method now. And the strategy is still the same. We define this auxiliary process. However, the algorithm is evolving by p hat, and the continuous process is evolving by p. So what kernel should the auxiliary process evolve by? And the answer we came to, the conclusion is that this auxiliary process should evolve by the ideal kernel P. However, if you only evolve by the ideal kernel P, it poses another issue, which is that this auxiliary process evolves by P. We're trying to hit a process that follows a different kernel P hat. So you can't actually guarantee that these two processes would hit exactly at the terminal time. And that's why what we do is we modify this auxiliary process to use p hat at the very last step. So we only use p hat for the last step, and this is where you incur this kind of cross-regularity assumption. That's why that kind of shows up in the bound. But of course, like some kind of assumption like this needs to be there in order to control KL divergence for the algorithm. And then one final point is like, why is it that the case that our final bound depends on this weak error and strong error? And the reason why is the way that we control the distance recursion between the algorithm and the auxiliary process is building upon this original W2 local framework. So you can kind of think of our framework as stitching together this W2 local analysis with this idea of like shifted composition and auxiliary processes to upgrade to KL divergence. Okay, so that's all I wanted to say. Maybe now I'll say that actually like the real reason that I was interested in all of this is because I have this longer term project, which is trying to get warm starts for high accuracy samplers. basically, like, I believe that this will be a key part for understanding the optimal complexity of sampling algorithms. And this problem of obtaining warm starts really requires you to analyze algorithms in stringent metrics such as Kale divergence or Renyi divergence. So yeah, but at some point this project got way too complicated that we weren't sure that we could ever finish it. And so we needed to really split this into several parts. So in this paper, Shifted Computation 3, we handled the case of the basic lunch fund. We're currently working on the underdamped case, which would be the natural next step. And we kind of know how to do this, but it's also pretty complicated. So it might take some time to write it up in a clean way. And then we also need to extend to other divergences and so on. But hopefully, like when all of this is done, then we'll have a kind of systematic way to figure out this problem that I was originally interested in. Okay. Yeah, thank you for your attention.